5.4, solving special systems of linear equations. Okay, so the systems we've looked at so far in the previous sections all have one solution. So if you were to graph the lines that are associated with the equations, they intersect in one place, and so the lines intersect. And the xy pair at the intersection would be the solution to the system. But it's possible to have one of these other two scenarios, and these are our special systems. So sometimes we'll have lines that are parallel, and that means that they don't intersect. So there's no solution then. Okay. So this one would have, no solution. And then you can also have two different equations that give you the same line. So it's hard to see here. It just looks like one line, but you could draw the same line on top of itself because you might have two different equations and get the same line out of them. And that means any point on one line is going to be on the other line as well. So there's an infinite amount of points, of solutions here, because all of the points on the line are solutions. So I'm going to say here the lines are the same. You have two different equations for the same line. Okay. All right. So you can solve these by graphing. That would tell you if you've got one of these situations. But you can also solve these by elimination or substitution, and I'm going to do both of those. And one thing you want to look out for, I'm going to solve these first two with elimination because they're already lined up with the x's, the y's, the equal signs, and the constants in both of them. And what's going to happen is that both the x and the y are going to eliminate at the same time. And when that happens, that means I know I've got one of these two situations. Okay? And you'll be left with a statement that is either true or false. So if you're left with a true statement, say you ended up with 7 equals 7. Well, that's true. And so if you got a true statement, then there are infinite solutions. Okay? If both the variables eliminate and you're left with a false statement, then, so say we had 7 equals 6. Well, that's not true, right? 7 does not equal 6. So then we'd have no solution. And that means we would therefore have parallel lines. Okay? So let's try out some examples here. So, I'm going to solve the system. If I just added these two equations together right now as they are, the x's aren't opposites and the y's aren't opposites either. So let's try to get the x's to be opposites. So I'm thinking, okay, to get those to be opposites, I'd want to multiply the top equation by 2 because then I'd have 4x and negative 4x. Okay, so I'm multiplying this top equation by 2. I'm going to leave the bottom equation alone, but I have to double everything in the top equation. So now I've got 4x minus 6y equals 6. And then for the second equation, I'm just rewriting it as it is. Okay, and then when I add these together, the x's canceled just as I suspected, but the y, or I wanted to happen, but the y's are also going to cancel, and even these constants cancel. So I'm left with 0 equals 0. That is a true statement. Okay, this is true, and that tells me, okay, if I've got a true statement, then I've got infinite solutions. Okay, let's try another out here. So let's say I wanted to get the x's to be opposites again. I'd multiply the whole top equation by negative 2. I'm going to leave the bottom equation alone. So this would give me negative 2x minus 2y. And then let's see, negative 2 times 3 would be negative 6. Okay, I'm just recopying that second equation. And then when I add everything together, the x's cancel, so do the y's. So I'm just left with 0 on the left side. Here I've got negative 6 plus 5 would be negative 1. That is a false statement, right? 0 does not equal negative 1. And so that means I know I have no solutions here. Okay. All right, let's try a couple more. I think I'll use substitution on these two just because they're not really lined up for elimination yet. I could rearrange them, but I'm just, for some variety, I'll go for substitution. So I want to get one of the variables in one of the equations isolated. And I can see in this top equation, the y is already isolated, so I'll just go with that. Okay, so y is equivalent to the quantity negative x plus 3. So then in the other equation, I'm going to substitute negative x plus 3 in for y. So I've got 2x plus 2 times the quantity, negative x plus 3. Use those parentheses so that you'll remember to distribute. Now I want to solve this because there's only one variable. I should be able to solve this for x, so let's see what happens here. Got negative 2x minus 6, or plus 6 rather, equals 6. Okay, and now 2x minus 2x is 0, so I'm just left with 6 equals 6. So those x's eliminated themselves again. And so now I've got this true statement. So since I don't have any variables left, I know I've either got infinite solutions or no solutions. This one is going to be infinite solutions. Infinite. Forgot the I there. Solutions. Okay. All right, let's try one more. The y is already isolated in the top equation. Y is going to be equivalent to that. So I'll substitute that quantity into the second equation where the y is. So I've got 10x plus the quantity, negative 10x plus 2 equals 10. Okay? And this would look the same without parentheses because we're just adding this. So when I combine 10x and negative 10x, they're just going to cancel out. And then I'm just left with 2 equals 10, right? Because those cancel each other out. 2 equals 10? Well, that's not true. 2 does not equal 10. That means I know I've got no solution because I got a false statement there. That's it for the section, and I'll see you next time.